Hi everyone, this is a group project titled Vibrational Behavior of a Jacket Type Offshore Structure Under Environmental Loading, and these are our group members. A jacket platform serves as the stable foundation for many offshore oil and gas or wind energy facilities. One of the main characteristics of this kind of platform is it is anchored to the seabed with piles in a relatively shallow water region, which is up to 500 meter. And this is why this kind of structure is pretty common in Malaysia sea area. And then the vibrational behavior of this kind of platform can be complex because it is subjected to at least four types of sources of vibration, including wave, current, wind, and seismic energies.
Hello, Dr. Kang. I am CHEng. For the wave loading is a dominant environmental load on the offshore jacket platform, and ocean wave apply time-varying hydrodynamic force that induce the vibration and fatigue in the structure. As the water depth increase, the natural frequency of the jacket decrease and may approach the wave frequencies, increasing vibration response. Since the wave loading is random and cyclic, the platform behaves as a forced vibration system influenced by the fluid structure interaction. Okay, for the wave spectrum are used to represent the energy distribution of ocean wave. Common model include the John Swart spectrum for real sea condition and the Pearson-Muscovich spectrum for fully developed seas, and the Orchid Harbor spectrum for mixed swell and wind seas. And this spectrum help define the wave energy that governs dynamic loading and vibration response of offshore jacket platform. Okay, for the type of wave loading, the wave loading can be classified into regular and irregular wave loading. The regular wave loading is deterministic and represented by a single repeating sinusoidal wave, mainly used for understanding vibration behavior, sensitivity study, and model validation. In contrast, irregular wave loading represents a real sea condition and is described using wave spectrum such as a John Swart or Pearson-Muscovich. A structural response under irregular wave are evaluated statistically, making this approach suitable for operating at an extreme sea state analysis. Both types may include nonlinear second-order effect that influence the dynamic response. Okay, for the offshore jacket platform, wave loading on slender member is commonly calculated using Morrison equation. The total wave force is the sum of inertial force related to the water acceleration and the drag force related to the water velocity square. Okay, for this slide, where wave kinematic describe the motion of water particle caused by the wave, including the particle velocity and acceleration. This motion directly generates the hydrodynamic force on jacket members, acting as an input excitation for structural vibration. And the wave kinematic varies with time and depth, producing the oscillatory force that are strongest near the free surface. And the wave period control the forcing frequency, and when it approaches the natural frequency of the jacket, resonance may occur. In the real sea, the random wave kinematics leads to a broadband vibration response. Okay, for this slide, the wave loading causes two main vibration effects on jacket-type offshore platform. The first, the wave-induced vibration arises from irregular sea wave, where the fluctuating water particle velocity and acceleration excite the natural frequency of the jacket, and producing the broadband vibration and fatigue damage. Then secondly, the voltage-induced vibration occur in slender member due to alternating voltage shedding. When the shedding frequency approaches the natural frequency, resonance can occur, leading to large oscillation and accelerated fatigue failure.
For current loading, there are several sources of currents that are identified to contribute to current loading. The first one is storm current, which is usually caused by wind and atmospheric pressure gradient during storm. The second one is tidal current. The third one is eddy current, which is the small circulating current located away from the main ocean circulation current. So the fourth one is the ocean circulation current, which is normally due to the circulation flow in the ocean. The fifth one is Soliton current, which is due to the density difference between sea waters, and the last one is the longshore current. It is generated by wave breaking phenomenon when waves reach shore angle at an angle. It is significant at near shore region. So for the effects of current loading on offshore fixed structure, the first one is it is cause scoring at the seabed. Scoring at the seabed weakens the foundation of a platform. So the exposed structures to the seawaters can cause vortex-induced vibration to occur at it, and it actually affects the stability of the steel structure. So current loading also causes vortex-induced vibrations. This is due to vortex shedding occurs when sea current flow through the steel frame of the platform, which induces lift and drag forces, and the magnitude of vortex shedding increases as the current velocity increases. The third one is the fluctuation in drag force in submerged component. As pointed out by Baojek et al. Studies in 2022, current is the main source of drag force on offshore fixed tubular structures. And the fluctuation of drag forces is also a source of vortex-induced vibration in submerged structures. By the studies of Hu et al. In 2020, current it has dominant effects on dynamic loading on offshore fixed structures at wind speed lower than 20 meter per second situation. So the current profile is very important for us to determine the velocity of overall current. According to the DMVGL recommended practice C205 and Faultison, the current velocity at a given point is the summation of all current components present at the point. So we could see it from the equation, it is purely a summation of velocity of each component of the current. To calculate the mean drag and lift force exerted on offshore slender structures, we could use the two equations as shown below given by Molin.
Different from the previous wave and current laws, wind load is more critical to the exposed topside structure above the sea surface. And wind load calculation is typically exclusive to all the structural members at the mean water level, as suggested by the picture. And wind load usually only contributes less than 10% of the total load. So the wind loading analysis can be quite complicated because usually this kind of structure, it is immersed within the ABL. That's why it is affected by the wind shear effect, which is meant by the variation of wind speed with vertical height. So this is one way to express the ABL profile, which is a logarithmic equation. And then, as you can see from the figure, the wind speed not only vary vertically or horizontally, but it also varies in direction. That's why accurate assessment of wind speed usually requires complex tools like wind tunnel tests and CFD simulations. There are two primary vibrational behavior induced by wind loading. First one is across wind vibration, which is caused by vortex shedding, the oscillation of fluid passing through a bluff body, and it is perpendicular to the wind direction and typically critical in slender members such as desk columns. And the main effect is fatigue to the structure. The other one is along wind vibration, which is caused by gusts along the wind direction. This kind of vibration has a low frequency, but the loading is pretty dominant for the vibrational response. And the effect is the global swaying of the jacket. So from the past findings here, you can see that the ratio of across to along wind load is about 10%. So that means along wind load is typically 9 to 10 times of the across wind load. Thus, it is more dominant.
For the seismic loading, the nature of seismic loading is a rise from ground motion transmitted through seabed and bites into the jacket structure. It acts as a base exciting dynamic load and it is different from wind or wave loads, meaning effect overall lateral displacement and global bending of the platform. For the characteristic for the seismic loading, it is a low frequency, long period motion. It may excite the platform fundamental moods. It also can have a horizontal and vertical component depends on site condition. It responds influenced by soil-like structure interaction or soil seabed, amplify displacement and bending. For the Malaysia, we can see that in the figure, Malaysia is in low sensitivity region. So the sensitivity is not a governing root but must be shattered for completeness. It evaluated using the equivalence static sensitivity analysis. The soil structure interaction is improved well simplified foundation stiffness. When we analyze the offshore jacket platform, we can no longer look at the earthquake alone in the insulation. So we must account for nonlinear superposition. The structural response under combined wind, wave, current, and earthquake is not a single additional of the force because of the complex interaction between the water and the steel frame. Those rows amplify each other not linear. Secondly, there is a significant rise of underestimation. If we do not wave action during a seismic event, we may dangerous understating the platform's stress and the displacement. Finally, the structural aspect, the distinct frequency characteristic under combined load. The platform vibration pattern changes when it is hit by multiple force simultaneously compared to a single load. For the advanced simulation method, to execute the assess safety, the research used the Copper Brubaker model to simulate the complex fluid structure interference with CFD FEA coupling. And it is involved the combination CFD to model environmental load like a wave and current with the FEA to calculate the structural response to successive flow acceleration.
So next, let's review the case of using a CFD FEA model, which considers fluid structure interaction effects to study the vibrational behavior of jacket offshore structure against many loads. And the loads involved in this case study are wind, wave, current, and also earthquake. So some brief methodology of this case, the wave is modeled as nonlinear, which is known as Stokes wave. And then the domain is a water tank, making this a multi-phase flow simulation. consists of air plus water. To validate the simulation model, one cylinder column is put into a film like this and compared with the past study, and it is shown that the wave loading contour is pretty similar, so it is validated. And this is a configuration of this simulation, the model, and then the final speed can go to 0.2 meter.
The offshore jacket platform model given in the case study by Lin et al. In 2024 is the model height is 105 meter, the tubular column thickness is 0.09 meter, and steel is used as the overall structures. It has a modular elasticity of 210 gigapascal, Poisson ratio of 0.3, and yield stress of 250 megapascal. So the boundary conditions for this model, it is separated into two domains, which is the fluid domain and the air domain. So for the fluid domain, depth is 66 meter and the air domain height is 50 meter. From the study, they have obtained average mesh skewness of 0.84, which is considered good. And to model the pile and foundations interactions, they use equivalent pile method at the platform legs. To model the wave and currents, the study actually uses the Stokes second order wave theory, where the wave height is set at 4 meter, wavelength is set at 50.5 meter, the current velocity is set at 1 meter per second, and the wind velocity is equal to 10 meter per second. So in this study, the authors did model analysis for the first 6 modes, and the result is validated against the equation of natural frequency of tower structure provided by Jeanette et al. In 2022 studies, and the equation is shown in the slides.
Okay, this part explains how environmental loading generates the vibration in an offshore jacket platform. The CFD simulation is used to apply wind wave and current simultaneously, creating a realistic hydrodynamic excitation. As wave propagate, the repeated patches of wave crest and troughs produce a cyclic pressure on the jacket legs. When wave crest strike the legs, the wave run out occur, causing the sudden force peak that amplify vibration. And the velocity field show the strong turbulence and vortex formation around the legs, indicating the potential vortex-induced vibration effect. Okay, this part focus on factors that influence the vibration severity. Increasing the water depth significantly increase freight pressure and lateral hydrodynamic force, leading to higher vibration amplitude. The wind wave current force are time dependent and nonlinear, acting as a continuous dynamic excitation source. And this load can cause dynamic amplification and platform sway. And overall, the vibration behavior of the jacket platform is strongly governed by a freight structural interaction, pressure fluctuation, and environmental loading conditions.
This figure shows the dynamic response of the jacket platform under the earthquake load alone only. Means that there is no current wave or the wind load at the simulations. Then is the dynamic response of the jacket platform under the wind, wave, current, and the earthquake with the zero direction load. So we can see that the graph is increase the S displacement and the stress compared to the earthquake load only.
These are the references involved. And by that, it comes to the end of this presentation. Thank you very much for your attention.